All right. So here we're just going to go over, these aren't really proofs, but we're just going to go over maybe some evidence for the central limit theorem. So we'll talk about the central limit theorem, some, I guess, evidence for the central limit theorem for the sample mean x bar, and then we'll talk about evidence in favor of the central limit theorem for p hat. And I'm honestly not going to do a lot of writing here. I just want to show you some simulations, basically. So I'm going to use a tool in these videos called StatCrunch, which you don't have access to, and that's okay, because you don't need to follow along. You just need to kind of watch the video as I run some simulations. So in this first example, we're told that scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. It says use technology to help you describe the sampling distribution of the sample mean x bar by simulating the collection of 1,000 samples of size 9 and then of size 25. Okay, and then we'll do a different simulation with a skewed right distribution a little bit later. But let's head over to the simulation. Okay, so here we have a bell-shaped distribution, right? This is supposed to represent the IQ scores. The mean is 100, okay, and the standard deviation is 15. And we want to collect 1,000 samples of size 9. Okay, so my sample size here is 9. I'm going to simulate just taking 5 samples of size 9. And what's happening is the simulation is taking a sample and then it's computing the sample mean of that sample, right? So down here we're getting different sample means, right? This is our third sample mean, our fourth sample mean. And you can see that some of these sample means overestimate the population mean and some of them underestimate the population mean. But you can imagine that if we take a bunch of samples of size 9, let me do another one, that we're going to start to get a distribution down here of sample means. And what the central limit theorem claims is that this distribution down here in green, this distribution of sample means, what the central limit theorem claims is that this distribution is going to be bell-shaped. Okay? It also claims that the average of these sample means is going to be the same as the population mean, and that the standard deviation of these sample means is going to be the population standard deviation divided by the square root of our sample size. Okay, so let's see if we simulated taking 1,000 samples. Now, fortunately, we don't have to sit here and watch it collect the samples individually. It'll just do them all at once. Okay, so I clicked on 1,000 times, and now this is after taking 1,000 samples of size 9. This is a simulation of what we would get. Okay, so you can see that sure enough, the average sample mean is equal, well, roughly equal to the population mean. Okay, and the average or the standard deviation of the sample means is about 5. Okay, well, the population standard deviation we started out with was 15, and our sample size was 9, right? Well, the square root of 9 is 3, and 15 divided by 3 is 5. Okay, so that seems to be holding up. And of course, the shape of the distribution is bell-shaped. But that's not super surprising because we were drawing from a population that was already bell-shaped. Okay, let's see what happens if we change the sample size to 25. Okay, so I can take one sample of size 25, okay, and it'll compute the sample mean. I can do this 5 times, and we start to get a little distribution down here. I can do it 1,000 times. And what I end up with is, sure enough, a bell-shaped distribution. The average sample mean, right, the mean of the sample means is 100, okay, approximately. And the standard deviation is about 3. Well, the square root of 25 is 5, and 15 divided by 5 is 3. So that seems to be holding up, okay? So it seems like the central limit theorem holds pretty well whenever you have a bell-shaped distribution that you're drawing from, okay? Now you can write some of those things down, some of those observations down here. I'm not going to really write anything. But the next example says, suppose you have data that's skewed right. Okay, use technology to help you describe the sampling distribution of the sample mean x bar by simulating the collection of 1,000 samples of size 4 and size 49. So let's go back over. Okay, so here I have a right skewed distribution, and I'm going to simulate taking a bunch of samples of size 4. Okay, so I can do 1 sample of size 4. I can do 5 samples of size 4. And again, they're going to compute. It's going to compute the sample mean and drop the sample mean down here for me. Okay, and so you're going to get this distribution of sample means down here. And we're interested in knowing the shape, center, and spread of this distribution. So let's go ahead and simulate if we had done this 1,000 times. Okay, so we get a distribution that looks something like this. I wouldn't necessarily call this a bell-shaped distribution. I would call it a skewed right distribution. However, it's not quite as badly skewed right as the data we started out with, right? I would also point out that the mean here is about 14, right? The mean of the population that we're drawing our sample from is about 14. Well, the mean of our sample means, right? The average sample mean is also about 14. Meanwhile, the standard deviation is about 12, and our sample size was 4, right? Square root of 4 is 2, and 12 divided by 2 is 6, right? So things are lining up. It seems like the mean of the sample means is the population mean, and the standard deviation of the sample means is the population standard deviation divided by the square root of our sample size, just like the central limit theorem would predict. The only thing that hasn't happened here, though, is that our shape is not bell-shaped. And that's because we have a small sample size, right? We're drawing from a population that is not bell-shaped, and we have a small sample size. So what we're ending up with here is not bell-shaped. But let's change the sample size to 49. Okay, so if I simulate taking a sample of size 49, or taking 5 samples of 49, or 10, or 1,000, well, now I'm ending up with something that's much more bell-shaped, okay? Which is really kind of amazing. It's kind of amazing that we're drawing our population from a right-skewed distribution, but we're ending up with a bell-shaped distribution when we take the sample means of all of those samples. So anyway, so that I think kind of verifies the central limit theorem for the sample mean x bar, right? For each part, mu sub x bar is about the same thing as mu, sigma sub x bar is about sigma divided by the square root of n, and for the IQ example, up here, right, for even when we had a small sample size, like when n was 9, we still ended up with a bell-shaped distribution because the distribution we were drawing from was bell-shaped, okay? Whereas here we had a right-skewed distribution, okay? And so when we had a small sample size, the distribution of the sample means was right-skewed. But when we had a larger sample size, it became bell-shaped. Okay. Let's look at kind of some evidence in favor of the central limit theorem for p hat. This one is even more strange in my opinion because for p hat we're going to be drawing from a binomial distribution, right? A binary distribution, and yet the claim is that when we collect all of the various sample proportions, we're going to get something that's bell-shaped, okay? So what I'm going to do is I'm going to set up a simulation where we have a binary distribution where the probability of success is 76%, okay? And then we're going to simulate collecting a bunch of samples. We want to collect samples of size 10 in part A, and in part B we want to collect samples of size 60. So let's do that. So here we have our simulation. We have a 76% chance of success, okay? And I can simulate taking a or I'm sorry, let me reset this. I can simulate taking a sample of size 10. Okay, if I do one sample of size 10, ooh, they were all successes in that sample. Okay, because there's a 76% chance of success. Now let's do another one. Ooh, okay, so 9 successes and 1 failure. We can simulate another one. Ooh, a bunch of failures that time. Okay, and down here, what's being calculated is the sample proportion, right? These are the sample proportions. We could do this 5 times and just watch the sample proportions get collected. And what we're interested in is, what is the shape, center, and spread of this distribution down here? Okay, so so far it's looking maybe a little bit skewed to the left, but let's see if we simulate 1,000 of these, or maybe 10,000 of these. Okay, definitely there is a little bit of left skew to this. As far as the mean of the sample proportions is concerned, notice that the average sample proportion is approximately equal to the population proportion we started out with, right? So in other words, if you take all these sample proportions down here and you compute their mean, what you end up with is dead on, well, pretty much dead on, the population proportion we started out with. The standard deviation is harder to see, but I bet if you took the square root of 0.76 times 0.24 divided by 10, then you would get this number approximately. The shape is still concerning though, because it's not bell-shaped. And once again, this is because we have a small sample size. If we change this to a sample size of 60, I bet we get something a little bit closer to bell-shaped, right? So here's the distribution now when we're using a sample of size 60. Or we could do 10,000, right? There's a little bit of a tail out here, but it's pretty darn symmetric, pretty darn bell-shaped, okay? So anyway, hopefully that that kind of convinces you that the central limit theorem is also true for the sample proportion, right? If you take a bunch of samples and compute the sample proportions and then make a distribution out of the sample proportions, well, if your sample size is large enough, you'll end up with a bell-shaped distribution, okay? Just like the central limit theorem predicts. So that's all I wanted to say for this particular little bonus video. So I will check in with you in the last section of material here, and have a great day.